In this video, we're going to talk about composition of functions. So composition of functions is when the output of one function is used as the input of another. And we call that particular operation a composition of functions. Now, we do have a special notation to notate composition of functions, and it looks like this. F and then open circle. So that reads mathematically F composed of G of X equals, and often they put parentheses around that, equals F of G of X. In other words, we're plugging G of X into F of X. Or similarly, G composed of F of X equals G of X. So written like this, it seems a little bit daunting, but it does make sense when you get to go ahead and try some examples. So let's look at some examples here. Suppose C of S represents the number of calories burned doing S sit-ups. So it makes sense that you're talking about how many sit-ups is going to burn how many calories. S of T gives the number of sit-ups a person can do in T minutes. So then we have another function that talks about how many sit-ups an individual can do in a certain period of time, particularly in minutes. So let's interpret C of S of 3. So let's start by what S of 3 means. So I like to start inside with this. So S of 3 means the number of sit-ups in 3 minutes. So it's however many sit-ups this individual can do in 3 minutes. So if I have that number and I take it and plug it into C of S, that's how many sit-ups there are, right? I'm sorry, C of S of 3. So I'm plugging that into the calories function. That means that this is going to tell me how many calories are burned in that 3-minute period. Wow, that's not how you spell calories. Calories burned in 3 minutes. And I'm going to abbreviate that just to fit it into one line. And that's a really reasonable idea. I would be interested in figuring out how many calories I might be able to burn in 3 minutes. So composition of function takes 2 ideas and kind of puts them together to make sense of something that we might be wanting to know. Let's look at another example. Suppose F of X gives miles that can be driven in X hours, and G of Y gives the gallons of gas used in driving Y miles. So let's figure out if this is meaningful to find F of G of Y and see if that makes sense. And then we're going to try the other way. We're going to find G of X. So let's start by G of Y, right? The first one. Let's look at F of G of Y. Okay, so G of Y is going to find gallons of gas after driving Y miles, however many miles there are. If I take that result, the gallons of gas, and I try to plug that into F of X, that's a problem. I can't. You see, X happens to be hours. This is not finding hours, it's finding gallons. So I can't plug this into F of X. Since input in this case needs to be hours. Okay, now let's try the other way. Let's see if it makes sense to find G of F of X. So F of X in this case is going to find the miles that's driven in X hours. So miles driven in X hours. And since G of Y is figuring out the gallons of gas based on how many miles you have driven, that makes sense because f of x is spitting out however many miles have been driven. So this does make sense. We can plug in to g of y. I'm running out of space, but there we go. So the first one does not make sense, but g of f of x, that makes sense. It's meaningful because plugging in the result that we get from f of x does correspond to the input for g of y. Okay, so let's look at compositions no longer from a theoretical point of view. Let's actually try evaluating these functions with numbers. So there's two tables. One is created based on f of x. The other one is created based on g of x. And we're given a few of the input values and their corresponding output values. And we're asked to find f of g of 3 and then g of f of 4. Okay, let's start with f of g of 3. All right. So first thing I'm going to do is I'm going to find g of 3. So g of 3 from the table is 2. So now I'm going to take 2 and I'm going to plug it in to f. So it's now the input for f. And f of 2 is 8. Oops. Still selected my highlighter. 8. So that would be the answer for f of g of 3. Okay, let's do it again, but let's do g of f of 4. So this time we're going to figure out what f of 4 is. Go ahead and erase all my highlighter. All right, so f of 4. So we're looking at the first table, and f of 4 is 1. So now I'm going to take 1, and I'm going to come back up here, and I'm going to plug it in to g of x. So g of 1 ends up being 3. And there we go. So what we're doing is we're finding the inside function, evaluating it first, and then taking that result and plugging it into the outer function. Okay, let's do this with a graph. Similar idea, but this time we're actually given the picture for f of x and g of x. So we're being asked to find f of g of 1. In the inside function, I want to find g of 1 here. This is what I want to focus on. Okay, so g of 1. That means I'm going to look at the second graph, the g of x graph, this one, and I'm going to figure out when x equals 1, that's right here, this thing is 3. So when we have 1, we get out 3. The x value is 3. Cool. So now I'm going to take 3 and I'm going to plug that into f. So I'm now going to look at the first picture here for f of x. And for f of x, then I'm going to look at where x equals 3. That's right here. And looking at the graph, that is going to be 6. And there we go. That's the result. So we're basically just looking for the ordered pairs right off of the graph this time instead of in a table. And it's the same idea as what we were doing previously. Okay, now composition with formulas is a little bit more involved. Before we get to composition with formulas, I want to do like a review problem here. Most of you have worked with function notation, but if you haven't, we talked about that at the beginning of the section. So let's look at function notation and let's look at some special examples. So let's start with f of 3. So that means we're going to plug 3 into t. So that's going to become 3 squared minus 3, which is 9 minus 3, which is 6. So that one wasn't too bad. F of negative 2 means we plug negative 2 in for t. And here, when we plug it in for t, it's going to become negative 2, which is going to be a positive. Okay, so negative 2 squared is 4. Negative 2 becomes plus 2. And again, we get 6. Okay, part C. Now, part C is actually boring. If I'm just plugging A in, that basically means I'm just rewriting it with a different variable. Not very exciting. Let's look at part D. Now for this one, we're going to do something a little bit more exciting. I'm going to plug x plus 2 in for t. So that means I'm going to have x plus 2 squared minus x plus 2. So actually, oh, sorry, this is the answer for part B. There's actually some algebra to be done. I'm gonna FOIL the x plus 2. So that's x plus 2 times x plus 2. So let's see, foiling that, x squared plus 2x plus 4. Oops, is going to give me x squared plus 4x plus 4. Here, we're going to actually distribute this negative in. So that's going to become negative x minus 2. Let's bring that down. And now we can combine like terms. So x squared. Okay, so these two are going to combine. That's going to be positive 3x. And then the 4 and the negative 2 combined to be positive 2. All right, and there we go. That is the reduced version of f of x plus 2. Okay, let's try f of t cubed. Now, this seems a little bit weird because we're plugging t cubed in for t. So I know it's not on my screen anymore, but remember we have t squared minus t. So I'm going to take t cubed, I'm going to square it, and then I'm going to minus t cubed again. T cubed squared, that's going to be to the second. You multiply those exponents, and there we go. That's fine. We don't have to factor our answer or anything. That's completely acceptable. We're just simplifying. And that's how we evaluate functions. Now that's useful for when we do composition of functions. So let's look at an example with that. So this time, we're given a f of x and a g of x. First, they're asking us to evaluate them at specific numbers. So part A and part B aren't too complicated. Let's start with part A. So we're going to evaluate g of 1. So first thing I'm going to do is plug 1 in for x in g of x. So that's going to be 1 over 1 minus 2 times 1. All right, so that's just going to be 1 minus 2, which is negative 1. So now I'm going to plug negative 1 into f of x. So that's going to be negative 1 squared, which is 1. So this work down here is I'm figuring out so that I'm figuring out what's this so that I can plug it in right there. That's the work that I'm doing. Okay, let's try part B. G of f of 2. So this time, we're going to first figure out what f of 2 is, and then we'll plug that in. So 2 squared is 4. So now I'm going to plug 4 back up here. I'm going to come back up here and plug that in for g. So g of 4 is going to be 1/4 minus 2 times 4, which is 8. And 1/4 minus 8 is 7 3/4, or another way of saying that is 31/4. All right. Okay, so now let's look at part C. So part C, we're being asked to find f of g of x. So we're going to plug all of g of x into the function f. So that means I'm going to plug 1 over x minus 2x into f. So that's going to become 1 over x minus 2x squared. Okay, so I got to FOIL this. Now I know that we're not used to foiling with fractions, but it's not too bad. I'll go ahead and kind of step us through. So if we multiply the 1 over x times 1 over x, that's just 1 over x squared, multiply straight across. 1 over x times 2x, the x's are going to actually cancel, right? Because you're going to have 2x over x, which is just 2, and it's negative. So that's going to be the same thing that we get here when we multiply those two. Negative 2. Negative 2x times negative 2x is positive 4x squared. Okay, so this becomes the simplified answer is squared minus 4 plus 4x squared. And that is the first composition. now they want us to go the reverse way. So this time we're going to plug x squared into g of x. All right, so let me write that down. So g of f of x means we're plugging in x squared, which means we're going to have 1 over x squared minus 2x squared. And honestly, there's not much we can do to simplify this. I suppose we could get them to have a common denominator, but on an exam, this would be good enough for me. You could go ahead and stop here. I'm okay with that answer. All right. Now let's look at one more example. This time we're kind of back to those real world examples that we were looking at. So a city manager determines that the tax revenue in millions of dollars collected on population of P1,000 people is given by this formula. Okay. And that the city's population of thousands is predicted to follow this formula, where T is years measured after 2010. Find a formula for the tax revenue as a function of the year. So in other words, rather than figure out what the revenue is going to be based on population, predict what the population is going to be and base that revenue formula on the year. All right. So basically they're asking me to take R of P and plug in P of T. So they're asking me to really take P and make that a P of T. So plugging in the function that finds the population based on time. All right. So let's do this. We're going to plug 60 plus 2t plus 0.3t squared into R. And R is going to be, let me write it below for space. So this is going to be 0.03 times all of this in the parentheses. That's what we're plugging in for P, plus the square root of all of that in parentheses. 0.3t squared. All right. So we could multiply the 0.03 into the initial one, but really it's not going to give us much to simplify. So let's just do that really quick. 0.03 times 60 comes out to 1.8 plus, that's going to be 0.06t plus 0.009 t squared. And then we can't really simplify this under the radical. We're just kind of stuck with this. There's no more like terms. This would be the answer. Now, here's what's interesting. If I were to plug a value into t, like if I were to plug in, let's say 7, that means what I'm really looking at, since t is how many years after 2010, this would translate to being the population in 2017, right? Which means I'd be finding the revenue in 2017. So this is going to find the revenue in 2017. So I'm going to plug 7 into what I just did above here. So 1.8 plus 0.06 times 7, 0.009 7 squared, and figure this out by plugging it into the calculator. Now I've done that ahead of time. So I get out 12.079. Now remember, the revenue formula is millions of dollars. So this is 12.079 million. So that's how much revenue the city can expect based on the population in 2017.